Welcome to T2, day 19 of calculus. We are going to review related rates. Deborah is watching a balloon go up, and we already have our three words written down. The balloon was released at a point 60 feet away from Deborah, and it goes, we assume, straight up. Oh, and it even tells us it goes straight up this time. Doesn't always say that. If the distance from Deborah to the balloon is increasing, oh, it's going to tell us that this is increasing now at a rate of 10 feet per second, 10 feet per second. How fast is the balloon going up when it is 100 feet away from her? So we have X, we have Y, and we have Z. And it tells us that this is 60 right there. So we know dz dt, the rate of change of this distance right here, that's different than before. If the distance from Deborah to the balloon is increasing at a rate of 10 feet per second, so it's 10 feet per second, how fast is the balloon going up? So we want dy dt when it is 100 feet away from her. So when it's 100 feet, when z is equal to 100. When z is equal to 100. So now we need the equation, and we know that that is going to be x squared plus y squared is z squared. But one thing we know is x is 60 the entire time. So we can just say 60 squared plus y squared equals z squared. And I like doing it that way because it's easy to remember that since x isn't changing, that's going to be 0 when we take the derivative. So let's take the derivative, and we end up with 0 plus 2y dy dt equals 2z times dz dt. And what do we want? We want dy dt. We want dy dt, so we need to find values for everything else. Well, first thing we can do is we can cancel out the 2's and rewrite it a little bit. So y times dy dt is equal to z times dz dt. And we know dz dt is 10, so we know that this number goes right there. So we want it when z is equal to 100, so we can plug that in as well. So we end up with y times dy dt is equal to z, which is going to be 100 times 10, which is the dz dt. And we still want dy dt, so we need to find the y value when z is 100. We need the y value when z is 100. So we have 100 on the hypotenuse. We have 60 right here. And we need to know what y is. So you know that 60 squared plus y squared is equal to 100 squared. So y squared is equal to 100 squared minus 60 squared. And when you do this out, you can figure out that y is going to be equal to 80. Do the square root of it. It's actually a 3, 4, 5 triangle in disguise. It's 80. So what does that mean? It means that 80 times dy dt is equal to 100 times 10. So therefore dy dt is equal to 100 times 10 over 80. You notice I didn't multiply it out. So this cancels, so you can cross out the zeros there. So you end up with 100 over 8, which is 12.5. And this is how fast, which one is how fast is the balloon going up? So this is going to be 12.5 feet per second right there. I'm going to jump to a different shape, but the structure of these problems is still the same. It's picture, know, and want. Picture, know, want. You are challenged to inflate a spherical balloon. So you have a spherical balloon. Yay, not bad. It's not bad. Could be better. You're challenged to inflate it to 8 inches by maintaining a steady rate of radial increase of 1/2 inch per second. So the radius right here, the radius right there. So it says, when the radius is 4 inches, how much air per second must your lungs pump into the balloon to maintain the required rate of radial increase? So we know we want dr dt. We want dr dt to be 1/2 inches per second. And what do we want? We're looking for, we want to find, we just want one, it's already there. We want dv dt, that's the overall increase in volume, when r is equal to 4. When r is equal to 4. So the key here is you need to link radius and volume. So you need to know that the volume of a sphere is 4/3 pi r cubed. You just have to know that, memorize that. The volume of a sphere is 4/3 pi r cubed. So now we're going to differentiate that with respect to time. So that's dv dt, and this can just go on the outside. So I'm just going to put 4/3 pi right here. And then it's going to turn into 3r squared times dr dt, like that. Now which one We can cancel something here too. We can cancel the 3's if we want to. We can. We want dv dt. So we're looking for dv dt, so we need the rest here. We need the rest. Well, we know that dr dt, is equal to 1/2. So we can plug that in right there. So we end up with 4 pi times r squared times dr dt is 1/2 right there. And we want dv dt. Well, we know r is equal to 4. We want it when r is equal to 4. So what do we have here? 4 pi times 4 squared times 1/2. We don't even have to do any division. It's all on one side. So when you do this out, you end up with 32 pi. And this is a rate of change of volume, so it's going to be inches cubed per second, not feet cubed. Inches cubed per second. So the key here was remembering or knowing and now memorizing that the volume of a sphere is 4/3 pi r cubed. Let's go back to cones. Sand is poured through a chute at a rate of 10 feet cubed a minute and falls in a conical pile. So we're falling in a cone like this. So the sand is coming in and it's making that shape pile. And whose bottom radius right here, the bottom radius is always 1/3 the altitude. That's this height right here. That's this height. So we know that r is always equal to 1/3 h. That's one thing we know, always 1/3 the altitude. How fast will the diameter of the base be increasing when the pile is 10 feet tall? So we want how fast will the diameter, so dd, that rate of change of diameter, when the pile is, so when h is 10 feet tall. So we need to link together, we know, and we know the volume, the rate of, the sand is coming in at 10 feet cubed a minute. So we know that dv dt is 10 feet cubed per minute. So we need to link together volume and d right there. And we're going to do that by remembering what the volume of a cone is, and that volume is 1/3 times pi r squared h, So we've linked them together almost, because the diameter right there, diameter is not radius. We haven't quite linked together volume and diameter. We have radius there, but can we easily convert radius into diameter? Well, diameter is equal to 2 times radius. Diameter is equal to 2 times radius. So we'll keep that in mind as we keep going. So let's do that derivative, which we've done something similar before, where we just keep the 1/3 pi right here, and then we do the derivative of the first times the second plus the first times the derivative of the second. Now what do we need? What do we want? We want dd dt. So we're looking for a rate of change of diameter. And we're going to get that by looking at the rate of change of the radius here. So the way we can do that is looking back over here, right here, and take the derivative here, and you get d dt. The rate of change of diameter is going to be 2 times the rate of change of the radius, like that. So what does that mean? It means dr dt is equal to 1/2 the rate of change of the diameter. So we take this right now, we take this, and we plug it in right here. We plug it in right there. So what do we end up? We end up with this. We've taken this, we've turned it into this, and now the reason that's important is we now have a link between volume right here, and we have dd dt, which is what we want. We want the rate of change of diameter right there. So what are we solving for? We want d dt, so we want this thing right here. The colors are getting all messed up right there, so we need to get rid of everything else. So we need the radius, the height, things like that. So we know when h is 10, so that is going to be 10 right there. We also know that the radius is always 1/3 the height. The radius is always 1/3 the height, so that r right there is going to be 10/3. So we've gotten rid of that one, we've gotten rid of that one. Now what about dh dt? What about dh dt? Oh, there's the radius again, so we need to plug that in right there. It's going to be 10/3 right there. We've gotten rid of everything we want to except for this dh dt. Well, that's where we use this again. If we take the derivative of this, we end up with dr dt is equal to 1/3 dh dt. And that tells us that dh dt is equal to 3 times dr dt. But we want dd dt, so we know dr dt is equal to 1/2 d dt. So you can take these two things and combine them. So we know that 1/2 d dt is equal to 3 times dr dt. So what does that mean? Sorry, dh, excuse me, I substituted in the wrong place right here. It goes in right here. So we know dh dt is equal to 3 times 1/2 of dd dt. So this is equal to 3/2 times dd dt. So that means that dh dt is equal to 3/2 d dt. So we can substitute that in right there. So what does this mean? Let's do all those substitutions, and all we'll be left with is dd dt. So if we do that with one more substitution, we know that dv dt is that one right there. All I've done is I've substituted in everything we need to know. So now if you factor these out, if you factor out the ddt's and do the division, you do end up with a relatively nice answer, but you need to use your calculator to get a decimal. You end up with 0.191 feet per minute. Now, when doing this, you might say, like, this is a ton of substituting. We kept on working on this one right here. Let's go back to what we had right here and see if there's another way to do this one, another path. Well, everything seemed to be okay from above there. Then it got kind of nasty. Well, let's look at this, for example. Let's look at this. We know that the volume is 1/3 pi r squared h, and then we had to use the product rule, and it got kind of nasty right there. Is there any way to avoid that? Well, we know that r is always equal to 1/3 h. We know that r is equal to 1/3 h. So if r is equal to 1/3 h, let's do the substitution now. So volume is equal to 1/3 pi r squared times 1/3, excuse me, times, if we're substituting in for, what does that mean? H is equal to 3r. It's equal to 3r right there. So we've written it entirely in terms of radius. And the hint that that might be helpful is that we're trying to search for a rate of change of diameter. And is there a really nice relationship between diameter and radius? There is. So what this means is we've gone from 2 variables to 1 variable right there. Let's clean it up a little bit. We end up with 1/3 pi r cubed times 3. But those 3's cancel, so you end up with v is equal to pi r cubed. Volume is equal to pi r cubed because of this relationship. We haven't even done the derivative yet. This is super helpful because now we have one variable. So when we take dv dt, we end up with pi times 3r squared times dr dt. Now we know we're trying to find, we know that dv dt, it tells us over here dv dt is 10. It tells us that it's coming in at 10 feet per minute. So we know it's 10 equals pi times, well, it's when h is equal to 10. It tells us when, well, it'll be h is equal to 10, but r is always equal to 1/3 h. So if h is equal to 10, that means that r is equal to 10 over 3. So that's 3 times 10 over 3 squared times dr dt. So if you do this out, you end up with dr dt is equal to 0.0956. But that's the rate of change of the radius. But we know that 2 times the radius is equal to the diameter. That's from here. So what you can do is now you know that 2 times dr dt is equal to dd dt. And we want dd dt, the rate of change of the diameter. So all we need to do to this is double it. If that's the rate of change of the radius, we need to double it to get the rate of change of the diameter. So that means that dd dt is equal to 2 times that, which is 0.191. That's going to be feet per minute. So the lesson here is you have to do lots of substitutions, but the earlier you can substitute, the better. The earlier you can substitute, the better.